Hi, I'm Ben-Yaakov. This presentation is entitled Amazing FEMM Simulation of Closed-Loop Current Sensor. I'd like to acknowledge that this work was done in collaboration with Evgeny Smidotsky, who ran actually the finite element analysis and simulation, and some of which are shown in this presentation. Now, closed-loop current sensors are built around a toroid or some other closed core. There is a gap in which there is a sensor which is sensing the magnetic flux density. This could be a Hall effect or a flux gate sensor. And then we have feedback here, which is attempting to zero this difference so that B will go down to zero. And this is done by injecting current to a secondary of N turns, such that N times I eventually is equal to IP. IP is the measured current in this line here. So when this thing is a stable condition, then we know that IP is equal to N times IS, from which we can find out, of course, that IP is equal to N times V out over RS. So this is the basic idea of the closed-loop current sensor. Now, looking at the coupling between the primary and secondary, this is basically a transformer. And in the steady states, what we are going to have is the primary current here, it's the one turn, and then we have N turns of the secondary. And of course, at a stable state, this equation holds. So the question that I'm now posing is, what will be the voltage here? Okay? Well, it's kind of confusing. You have a current source here, you have a current source here. We can resolve it by looking now at the situation in which you have a short. Now, if you have a short, the voltage will be zero because you have a short, and the current will obey this relationship because this is a transformer. So therefore, we come to the conclusion that for the ideal transformer, the ideal case, if you have these two current sources at the input and output at the two sides, then the voltage will be zero. The question is, okay, but then what's going to be the magnetic flux density in the core that you are measuring? So if we look now in the more realistic case, in which the coupling coefficient is not 1, then we're going to have leakages here. This is the primary current, this is the secondary current. Then we have a magnetization inductance here. This is an ideal transformer as before. And here there is a question, is this relationship holding when you have these leakages? And in particular, perhaps you have a current here, so therefore these will not be equal. This relationship will not hold. Now, remembering that when the currents are equal, that is the N times I is equal to IP, then the voltage is zero. If the voltage is zero, then there is no current here. So therefore, even for the physical transformer, which has leakages, then even for this case, you'd expect that the voltage here will be zero. But again, does this mean that we are going to have in the air gap a magnetic flux density of zero? So now let's have a look at it from another point of view. We can draw a reluctance equivalent circuit here, magnetic circuit. What I'm showing here are two windings. There's a primary, one turn, secondary. We have the gap, and obviously we're going to have leakages here. Okay, so we have leakages here, and this will be then the equivalent circuit in the reluctance domain. We have the reluctance of exposed to the secondary. This is the primary. This is the leakages for each one. This will be the reluctance for direct leakage here, and this will be the reluctance of the gap. And we are measuring the voltage across this resistor. This is the magnetic flux density. Now, obviously, if this structure is symmetrical, that is, these leakages are the same and these are the same, then we are going to have zero here. There's no question about that. But do we have symmetry here? That's a big question. Well, it seems that we cannot answer this with the electrical equivalent circuit or with the reluctance equivalent circuit. We do have to go to finite element analysis. That is to look actually at the magnetic flux density inside the core and see what really is happening. Now, we have been using the FEMM, which is a free package, highly recommended, and the results we're going to show are actually results of simulation with FEMM. So to do it more realistically, we've chosen a core here. This is the core. The outer diameter is 23 millimeters, and the height, this is here, is 7 millimeters. And we have chosen the material of 3C94. And here is the window of FEMM in which you put the information. Let me skip this thing, which is not that important at this point. And also, we need to feed in the approximation of the BH curve. So we did some fitting to the data sheet of this material, 3694. And what you see here is the fitting that we got, which is pretty good. And you see that this core is getting into saturation at about 0.45 Tesla. This is Tesla here, and this is ampere meter. So the first run is putting the secondary here. We're putting 10 turns, a gap of 1 millimeter, and the primary is in the center. This is the wire that we want to measure the current of. It's in the center, and we have 10 turns here. Now, if we are passing 10 amp in the center wire, that is the current that we want actually to measure, and there is no secondary current, then we're going to see this flux within the core, and the maximum here is about 20 millitensor, and this goes now this way, the magnetic flux. Now, if we pass current only at the secondary, at the right value, that is 1 amp because we have 10 turns, then we see again about 20 millitesla, and the current and the flux is going, of course, the other way if the directions are correct. Now, if we have both the current of the center wire and of the winding here, the magnetic flux should cancel out, but as you can see, it's not exactly, not at every point, okay? There are some remnants. Here, for example, we have 3 millitesla in this region here, quite a bit. But, lo and behold, in the gap, we have a very low magnetic flux density. It's about 2 microtesla only, okay? So, indeed, within the gap, we see the cancellation effect, while in some other places, we don't see it exactly. And the reason, of course, we'll discuss it later on, is the high reluctance that we have here. So here is just the direction of the fluxes. Clearly, we have flux going this way, and then here it's going this way. So this is why they are sort of canceling each other. And again, here in this void here, in this gap, it's very, very low. Now, what happens if there is a mismatch of 5%? That is, the current of the compensating winding is a bit higher by 5%. We find that in the gap, we're going to see 0.6 millitesla. Okay, so it's an error. And of course, in the feedback system for measuring the current, we are going to bring this down to 0 by correcting the current here to such as this magnetic flux density here will approach 0. So here is a comparison between the case that we have a perfect match of the currents, and then when we have an offset, you see that with the offset we start to see the magnetic flux building up within the core and of course outside too. Assuming that we have a error of 0.6 millitesla 0.45%. What does it mean in terms of sensitivity, or you might say offset or zero of this measurement of being in relationship to the current? So 5% of the secondary is about 50 milliamp. This comes to be 12 millitesla per amp, or 1 microtesla of mismatch corresponds to 80 microamp. This is 0.008% or 80 ppm. So the sensitivity is very good and the offset is very good, and perhaps even it's better than we see it here, since we have very finite resolution due to the simulator. So this is just the first order approximation. Now what happens if we move the center wire away in a sort of asymmetrical case? Well, it is still very low. It's a little bit higher than we had it before, but really not much. Okay, instead of 0.6, we have it 1 microtesla when this is offset up to here. Now we're going to spread the wires rather than concentrate them in one place and see the effect. And here it is. You see the wires spread out, and here is the center wire. In the ballast case, again, here it's very, very low. It's about 0.6, 0.8 of a microtesla. Very, very good. Now, let's do some more experiments. Let's see how is it sensitive to frequency. There is this option that you can have in FEMM. So this is for 0 frequency. Well, we see it a little bit higher. Again, it could be a resolution of the simulation. And then at 100 kilohertz, it's about the same, meaning that really the higher frequency does not make any big difference in this case. Now, what about having a center wire which is much, much larger, occupying just about all the void, all the hole here in the ferrite core? And this is for the spread secondary. We have it here. You see, this is the primary, again 10 amp, secondary is 1 amp, 10 turns, again very low. Well, it's a little bit higher than the 0 we have seen earlier, but still it is fairly low. Then we concentrate the wires here with a large center wire, and here is what we get. Basically the same thing. Doesn't make a big difference, okay? So we still see 4 microtesla here, and here we see a higher magnetic flux density, but as far as detecting 0 magnetic flux density in the gap, this seems to be pretty good. Now what if we increase the current? Well, basically we shouldn't see any difference, but the problem is that even when there is a good match between the primary and secondary current, or ampere turns I should say, we see here, in this case for example, a higher magnetic flux density, which means that if the current will be high and high and high, then eventually we might actually saturate this region, and therefore the situation is really changing because like we have another gap here. So here is the case with the spread wires, 1000 amp. Still we are in good shape here. And here it's 2000. Now the magnetic flux density is building up here, and it's already getting to 0.3. Now 0.3 is pretty close to the saturation, and therefore we start to see here an error. So the higher current by itself should not make any difference, but it makes a difference because the core is now moving towards saturation, although the ampere turns are okay. You would have thought that if the ampere turns are the same, then there is no magnetic flux density left, but that's not the case. The fact is that in some region here, you do have a much higher magnetic flux density, and therefore it could saturate the core even though the currents are matched. As we go up to a much higher current, like 0.4, so we are actually approaching the saturation. You see a much larger error here. It's millitesla rather than the microtesla we got before. So this portion here is actually saturated. So therefore, we have like another gap here, and obviously the operation is messed up. And then, even going higher, this does not change very much, or only that a larger portion is now saturated, and we get a much higher error here of 50 millitesla, even though, of course, these are matched in terms of the ampere terms. Let's go back now to the question of the effect of the position of the center wire, the wire we want to measure the current of, and the secondary winding. So here I have it close to the gap already, and now we're going to do the maximum interference we can. We have put the wires across the gap, and the primary wire of the current that we are measuring is close by. And here I'm showing what happens if only we have current in the center wire. Here it is. And then what happens if we have current only in the secondary. Okay, in both cases we have the magnetic flux density practically confined to the core. Of course, the direction are the opposite directions. So therefore, they are supposed to cancel each other. And lo and behold, here is what we see. This is, in my mind, amazing. It's really amazing, because we have put the wires just on the gap. One would have thought that in this situation, the magnetic flux density in the gap will be much higher. And it is not. This is really, really amazing. So we get here only 0.7 microtesla within the gap, despite the fact that we have everything on it. So how can we explain something like that? This is really amazing. And my explanation is the following. In the videos that I have posted in YouTube, I've said many times that leakage is not part of a winding. It is in between winding. That is the flux that is lost in between the winding. And the example I'm giving is like a road between two cities. The road does not belong to one city or to another. It's something in between. So if we look at it this way, that this is the wrong picture, but that the leakage really represents the part of the flux which is not common, then no matter what, this structure is symmetrical. And if it is symmetrical, then the magnetic flux density in the gap here, which has a high reluctance, will be zero, no matter where you put these wires. So this will be my explanation. I don't know if it is correct, but this is my gut feeling that this is really what is happening here. Otherwise, I just cannot explain how come that we put everything on here and still we get this very nice response of almost zero magnetic flux density in the gap. So the conclusions here are that sensing B in the air gap is an excellent way to detect current balance. Very good. And the structural phenomena does not seem to be intuitive. It's not clear enough what is really going on, but the finite element analysis and the FEMM free package gives us an insight in what is really happening within the core. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.